Hello friends, today's question. A uniform cylinder of length L and mass m having cross-sectional area A is suspended with its length vertical from a fixed point by a massless spring such that it is half submerged in a liquid density sigma at equilibrium position. The extension x naught of the spring when it is in equilibrium is given by. So we are given a cylinder whose length is L and mass is m. So let us draw a cylinder whose length is L and mass is m, and it is submerged half in a liquid density. So it is submerged in half. So let us suppose this is a half. So this will be our L by 2 as well as this will be our L by 2, and it is fixed by using a massless spring. So let us connect a massless spring to it, and in the position of equilibrium let us suppose the extension in the spring is x naught. So there will be a force acting on upward direction that will be k x naught, and in the downward direction on the cylinder there will be a force will be acting in the downward direction because of the weight, that will be mg, and in the upward direction there will be also a force that will be the buoyant force. Let us call that as fb. So this is our buoyant force, and this buoyant force will be only you can see because of the cylinder that is submerged in the liquid. So it means it will be only because of the half of the cylinder, because only length L by 2 is submerged in the liquid, and sigma is the density of the liquid. And what else is given? It is capital L, not a small l. And we are given area of cross section is given as A. Okay, so we are given area of cross section is given as A, m is the mass. So from the figure we can clearly see that there are three forces that are acting on the cylinder. First will be your weight of the cylinder mg acting in downward direction, buoyant force fb acting on the upward direction, but that will be only half of the cylinder, and another one will be the spring force. So let us say that forces acting on the cylinder, forces acting on the cylinder three main forces. Three main forces. First will be weight of the cylinder, weight of cylinder, and it will be a downward force due to gravity. So we can say it is a downward force due to gravity, and let us call this as F gravity, Fg rather, and this will be equal to mass into g acceleration due to gravity, where m is the mass of the cylinder, m is mass of cylinder, and g is acceleration due to gravity. second force that will be acting will be the buoyant force. Buoyant force, and it will be an upward force exerted by the liquid on the submerged part of the cylinder. It is the upward force exerted by the liquid on the submerged part of the cylinder. So it means as the cylinder is half submerged, so it means the volume of the liquid displaced by the submerged part, let us suppose, is given as V displaced, and that will be equal to L by 2 multiplied by the area of cross section A. So you can say since the cylinder is half submerged, the volume of the liquid displaced by the half submerged part of the cylinder so let us call that as V displaced. So we have volume of the liquid that is displaced will be equal to length multiplied by area of cross section. Length submerged is L by 2, that is A, area of cross section. So from here we can find out that the buoyant force FB therefore buoyant force FP will be equal to density of the liquid multiply the volume displaced and multiply by G. So substituting, we get FP will be equal to sigma L by 2 multiplied by A and G, where sigma is density of the liquid, density of liquid, A is area of cross section, of cylinder, and the third force is the spring force. Spring force. And it is said that the cylinder is in equilibrium. So as the cylinder is in equilibrium, we can clearly understand or make a statement that the forces acting on the cylinder, net forces acting on the cylinder will be equal to 0. So we can write that at equilibrium the net force acting on cylinder is 0. So So downward force due to weight of cylinder is balanced by the upward force as well as the restoring force of the spring. Therefore, the downward force due to weight of cylinder is balanced by upward buoyant force, and restoring force of the spring. And restoring force of the spring is given as Kx0. Restoring force, and let us call that as F spring, and that is equal to Kx0. So in the figure itself, this is our restoring force, buoyant force, both are acting upward direction, and mg is acting in the downward direction. So therefore we can write that at equilibrium F gravity, that is Fg, downward force, will be equal to the buoyant force acting in upward direction Fb plus restoring force Fs acting in upward direction. So let us substitute the value. Fg is mg, will be equal to Fb is sigma L by 2a multiplied by g plus Fs is K x0. So from here we can find out our x0. Kx0 is equal to mg minus sigma L by 2ag. So we can write that our x0 is equal to g can be taken as common, so this will be g by k, and we have here m minus, and this will be sigma La divided by 2. And if we see the options that are available to us, the m is also taken as common. So let us take m also as common. So this will come as mg by 2, 1 minus sigma La divided by 2m. So let me write it here. We get x0 is equal to mg by 2 is 1 minus sigma La divided by 2. Sorry. So this is the extension in the spring at equilibrium. This is extension in spring at equilibrium. So we can say that, sorry, this is K, my mistake. Okay, and rest looks fine. So therefore we get that the option that is available to us is option number C is the correct one. Option C is correct. So in this case we found out that the option C is the correct, but we can also find out that this question can be further modified, that the position of x0 is the position of the equilibrium, and after this position of equilibrium, if the cylinder is slightly displaced further by a distance of x, then the cylinder is going to execute an SHM, and we can find out what will be the frequency of that SHM. Okay, let us consider a further modification, and we can also find out further kinetic energy, potential energy, as well as work done by the spring, or we can also find out the power delivered by the spring. So these are a few variations which we can do in this question. So let us make some, you can say, extension. And first extension is that oscillation if the cylinder is displaced by x from its equilibrium position. Oscillation after displacement by x from its equilibrium position so that it executes SHM. It executes SHM. So we are going to find out frequency of SHM. Frequency of SHM. Okay, so x is the extra displacement from its equilibrium position, that we have to keep in mind. So we can say that when the cylinder is displaced by a small amount x and released, it starts oscillating. When the cylinder is displaced downward by a small amount x, by a small amount x, and is released it starts oscillating. It starts oscillating. So in this case, now as it starts going to oscillate, the total restoring force is going to change. So therefore we can say that total restoring force now include both spring force and additionally the buoyant force also. Now include both spring force and additional buoyant force. Additional buoyant force due to displacement x. Due to displacement x. So please keep in mind that this buoyant force is acting as a restoring force only for this displacement x. Okay, it's not acting because of the entire volume. It is acting only because of this displacement which we have made an extra amount, that is x. Okay, so this is the key factor in order to, you can say, find out the frequency of oscillation, because the bound force from the position of equilibrium, it is displaced by the x. So buoyant force now will be additional, will be only because of this x, not because of the entire cylinder which is submerged. Therefore we can write that restoring force from the spring, restoring force from the spring let us call that as Fs, and that will be equal to minus k times x, and the additional buoyant force, now the cylinder is, you can say, moves downward by a distance of x. So therefore volume displaced will be equal to A into x, where A is the area of cross section. The cylinder moves downward by x, therefore the volume displaced by this displacement will be equal to A multiplied by x. So now we can find out the additional buoyant force. Therefore let us call this as FB. So we can say FB will be equal to sigma AX multiplied by G. In some of the solutions, we can also write in this way, that we can consider the entire displacement. In that case, the buoyant force will be equal to L by 2 plus x, and accordingly the slight modification required. In both the cases, the answer will be coming same. Okay, but in this case, the way which I have solved is I have taken the additional buoyant force, that is because of the displacement x, because rest I assume that it is in equilibrium, and the SHM will be only dependent upon the two forces. One is the restoring force because of the displacement x, and the additional buoyant force because of the displacement x. Okay. So therefore total restoring force let us call as Ft will be equal to our minus kx, and this will be minus axg, and taking minus of common, get Ft is equal to minus x plus sigma ax times g. So this is the total restoring force, and now it is in motion. So we can say that we can use the equation of the motion. Equation of motion, which means that our Ft will be equal to mass into acceleration, and that will become mass into double derivative of displacement with respect to time t. So we substitute it, we get this as mass double derivative with respect to time, and this will be equal to minus k plus sigma a g x, we can take as common, and a solution of this will be a, you can say, equation which represent a simple harmonic motion. So we can write this as double derivative of t square plus k, and we have sigma a g divided by m times x is equal to 0. So this is equation for, you can say, SHM. So therefore we get omega square is equal to k plus sigma a g upon m, or we can say omega is equal to square root of k plus sigma a g upon m. Omega is equal to 2 pi f. So we can write this as 2 pi f is equal to k plus sigma ag upon m, or we can say frequency of oscillation 1.2 pi is equal to k plus sigma ag upon m. So this is our frequency of oscillation. Now we can also find out what will be the kinetic energy as well as potential energy in this case. So let us first of all find out the kinetic energy. And kinetic energy we know is given as half m v square, which is also given as half m omega square a square minus x square. And potential energy will be equal to half k effective times x square, where k effective is the effective spring constant, because just now we concluded that the restoring force will be combination of the buoyant force as well as the spring. Okay, so k effective will be equal to, so we can say k effective is the spring constant in which buoyant force also contribute to restoring force. So therefore we can write k effective will be equal to spring constant for the spring plus we have it is sigma g a. Therefore the potential energy will be equal to half k sigma g a times x square. And we can also find out work done by the spring. Work done by the spring, and which will be equal to W is half, once again it will be k effective times x square. K effective we just found out, so this will be omega W, sorry, not omega but W is equal to half k plus sigma GA times x square. And we can find out the power delivered by the spring also. Power delivered by spring. So we can write this as PT will equal to Fs multiplied by the Vt, and Fs is our total restoring force. Sorry, let me write it Ft. Total restoring force. So I can write my Ft will be equal to minus K plus it will be sigma Ag, and that will be times x of t. And V of t we can find out. We can say V of t is equal to derivative of x of t. So we get V of t will be equal to minus a omega sine of omega t. So we get Pt will be equal to Ft we found out is our K plus sigma Ag xt, and Vt we just calculated. Let me write it. This is minus, sorry, this will be minus a omega and sine omega t. This is the power delivered by the spring. So these are the various combinations. There is furthermore combination also, and these are the basic combination which can be used with respect to the given question. This completes the finally the entire solution along with the various combinations. Thank you.